Okay, Brian and I are going to show you AZTEC, which is project actually out of the UCLA BD2P Center. There's a large team, so two of us just presenting to you. So I noticed that some of you may have heard an earlier version of this presentation, but if you have not, don't worry. So after Brian will give you a nice demo to show you what AZTEC is about and how to use it. And so we started last year. It's about a year-old project to create an index for the resource discovery. So what do we mean by resource? Means like software, the web services, APIs, plugins, so all the other resources. It's nice that actually today we learn a lot about like the data discovery side, right? So we think there's a lot of synergy point that we can form collaboration. So our goal is to make all those resources fundable, discoverable, okay, through the creation of an index. So this is the overall architecture. You can see that our vision here is that we first, need to discover all the resources. Some of those resources, especially those ones that are widely used, are being maybe already indexed by some other existing public repository. Okay, so if that's the case, so actually our first effort was to basically import all of those. We don't want to duplicate effort. We import all of those, and then we're also planning to go to all those repositories, code repositories, and hopefully in the future automatically to discover all those resources and create a proper index. And another source of the information we're thinking about would be the literature, right? People often like if I have a new software and then I publish a paper and I report that software, right? And in that paper, we may often find like this URL to the location of where people can either look on the web or maybe there's a GitHub repository, right? It depends on things. So we want to actually automatically discover that. So and then we will for the sake of time, I'm not going to go into the detail about the actual technology behind the scene. We have a database engine and behind, and then there is also a step for human curation to make sure the quality is up to the bar. And then once we pass through all these things, and then we publish the results so that everybody, the user, can query through a web interface. So far, these are the existing repositories we have been able to successfully import their resources, and this is totally, we have over 9,000 resources being indexed. Here are the list of some of the major features AZTEC enabled. The first one would be search, and Brian will show you some demo like you can see these are the usual suspects, like people often search by keyword or specific field, or maybe they want to put a search term like gene or protein, maybe they're too generic, and then realize there's too many resources pop up, and then from that you can further refine, search within the result of the search. You can do this successively until you find the one you want. And then the author can always submit new resources. If they said, oh, this one's not being indexed yet, either by manual submission and then realize that process probably not optimal, and then now we allow you can just upload a PDF, and then we can automatically extract relevant information from that file. And in order to do that, we have a logging system so that everything's done in a reliable and a secure way. And we also provide a way to provide feedback. If there's a bug or if there's a suggestion, you're welcome to do that. On the front page, we have a statistics, graphic statistics generated by the Google Analytics. So now, I think Brian is going to show you a demo of AZTEC.
Okay, just go to the browser for a second. Okay. Okay, so here's the homepage for AZTEC. As you can see up here in the corner, this is still in the beta version, so we're making a lot of regular changes. The main focus, as what I said, is the search engine for bioinformatics tools. So also I'm showing on the front page we have a lot of statistics available, usage statistics, and resource statistics describing the type of the composition of tools in our database. So if I search here, I can search for a term, and you'll see there's an autocomplete, and it'll either autocomplete showing a suggested resource with that title, or it could be a particular tag for a type of tool. I can select the tool and search. And we're going for a sort of an Amazon.com or sort of e-commerce style result page with filters on the left-hand side for people to filter their query. So I could come on the side here, and I could select a particular language that I wanted to limit the filter to, and you can see on the right-hand side the refinements are kept, and they have access so you can later remove those refinements if you'd like. And I can see here my top result is Lucid. So I'll click on that. Here's a description of the tool, information about the usability in terms of licensing, a link to the home page, publications associated with the tool, and the funding sources. We have to promote citability of tools to help try to encourage tool creators to have their tools indexed in AZTEC. We have a citation exporter that will automatically export in a BibTeX format. I also want to demo our resource registration and our login system. So in addition to mining repositories and mining PubMed, we also allow people to manually enter tools and also to edit tools that have been automatically mined from other sources. Here you can see things that I've submitted into AZTEC. I can go to the resource registration page. And as I mentioned, we have a PDF uploader that will automatically extract metadata from PDFs of journal publications, to automatically populate quite a few of these fields. I don't have a file to demonstrate that with me right now, but I'll show you some of the vocabulary control we have for this form. So, for example, if I'm trying to add an institution, we don't want everyone to just type everything in free text. That way, we're going to lose a lot of the quality of the metadata. So we try to always correct free text to establish vocabulary. So, for example, if I type in Caltech, here you can see California Institute of Technology, or if I type in California Institute of Technology, either way it'll link to the same entity to help maintain high metadata quality. So we have these control vocabularies for institutions, funding sources, programming languages, licenses, all sorts of things, and we'll go over those during the slides. One more important thing, because we are currently in a beta test, we're making a lot of rapid changes. Users might encounter some bugs or inconsistencies. So we have a feedback system that's integrated. So I could type in the description of an error I see. And then I could, so look, actually, something changed here with the formatting. Like I could highlight a particular portion. So it's strange. This doesn't seem to be working exactly that well on Firefox. We typically use Chrome. But I could black out a particular portion of the screen I didn't want to see, and then you'd have a screenshot with that blacked out, and then you could submit in the feedback. But yeah, there seems to be a bug with that right now. So that's basically that's it for the demo. So we'll go back to the slides.
Okay. Now I'm going to briefly go over like how we did currently the certain items that we're focused on. The first thing, as Brian mentioned, is the vocabulary control, and then there's issues of duplication, potential duplication. Because the one thing is that when we import resources indexed by existing repository, maybe there's a popular tool being indexed by multiple places. But if you look at their metadata of those tools, they may not be identical, right? So they have their own version, and then there may be some overlapping entries, but not exactly describing the same language. So we want to be able to identify that and somehow clean the record, merge the entries. And the same thing would happen if we start to actually at scale process all the publications, then some of the tools may be already been indexed, so we want to identify that. And once for each of the tools, we want to assign a domain, or at least one domain. So we want to be automatically determine what should be the domain. And also, in the future, we want to enable the search for similar tools. The tools may be developed by different research groups, but then serve the same purpose. Then we want to give us a recommendation. And also, we want to be able to properly rank the search results, especially for those popular areas. There's maybe many tools available. Then which one would be the most relevant? And also, how do we resolve the conflict between different sources of information? And last would be the publication monitoring. How do we automate this whole process, basically? So for the vocabulary control, and you can see that from this table, on the top half, those ones that we already finished, namely platform, institution, license, funding resources, BD2P relevance, basically which center you're from, and currently we're working on these biological domains and the resource type. So far we have 11 of those, and also the authors, and then input-output format of those resources. That's currently what we are working on. For the duplicate detection, basically we need that validated new resources and also to be able to identify replicates within the current database. For that, we basically need a way to identify very highly similar descriptions, either by name and by descriptions, by authors. And currently we're using a few heuristics, but then because this is a work in progress, we welcome any suggestion on that to see how do we identify the duplicates. So far it's been pretty good as a result. And the next thing is on the domain classification. So basically, if we have a new resource, we want to be able to automatically suggest what would be the most relevant domain that describes these tools. And we want to do this in an automated way through machine learning methods. And we have been investigating a few machine learning methods for this by treating actually the word in the description as the features. And so far we have been testing logistical regression. And then those are actually examples, and those highlighted, underlined ones would be the important word that actually relevant, for example, in this case for genomics. And also this is, for people from text mining field, TF-IDF would be the first thing maybe that people think of to try, basically using the term frequency and inverse document frequency to determine what would be the important features that describe each domain. And in his case, you can see the green upper arrow means important, and then the downward red arrow means like actually negative importance. So, and then actually current thing we're trying to see through the model topic modeling called LDA, and then basically it uses a probability distribution of words to describe domains. So this is a work in progress. And so far, I think our precision is about 80% by the logistic regression. We believe actually initial results suggest that LDA is going to do better than that. And in the future, we're going to have an integrated approach. Hopefully, can have an even better precision. So the next thing is that we want to be able to provide a similarity search for tools. Either by keyword or by other features. And our way is, try to think of something similar to Google PageRank algorithm. But in our case, because we are focused on the tools and with their descriptions, we use an algorithm called text rank. So to give you a brief idea, this is a small example showing like text rank determined on individual terms. But we're going to generalize that for sentences and for paragraphs and for tools. So the idea is basically we can create a graph of all the terms, showing example from a simple description of a tool. And then we can measure the importance of the rank of each individual term through the the frequency of its connection with other terms. Connection means co-occurrence in this particular case. And here, like one, basically RN6 has one connection with the resolution, and then the resolution has one connection with RN6, and then maybe counted twice with level, and then twice with the base pairs, and those are being normalized by the total count of those relevant terms. So, and then we do this iteratively when the actual algorithm converges after the importance, which means the rank of each term is determined. So this can be generalized to sentences and also to the level of document. So by that similarity search, and actually this is applied to the text rank algorithm to tools. Now, instead of using each word as a node in that graph, each tool becomes a node in that graph. And then we use a similar algorithm to basically determine how relevant each tool is. And this is basically you do RNA scheme, and then that's on the right hand side would be the answer. You can after part of the answer, because the answer may be quite long in this particular case that you are expecting. So of the search result, we want to be able to rank that. Maybe the most relevant we want it to be on the top, and then the least relevant to be on the bottom. This is especially important if there's people are searching in a popular area where there's a lot of resources already being developed. So, and this is a simple example. Like if somebody search RNA sequence and it's in a very popular term to be searched, and then you can see there's over 1,700 actual results currently indexed in AZTEC if you search that. And so if you just use a simple way to rank them, and then that's what you would see on the left hand side. You can see that well, there's a good result, but clearly the most popular ones is not ranked as the first. So what we hope to do is that what's being shown on the right hand side basically, and those ones are actually widely used, widely recognized to be relevant, the most relevant ones. So you can see top hat 2 and selfish. If you're coming from that area, you will notice that those are the widely used ones. So also we want to be able to support comprehensive search. Means that we want to leverage on the existing ontologies that define the semantics of the terms, and also we want to relax the search query to its synonyms and the hypernym and the hyponym, so that because sometimes especially the user doesn't know how to express a query. They may find, okay, maybe I should use this word because I know this, but then it's hard to be, maybe that may not be the best one match what's being in the database. We would automatically look for what is the proper relaxation that's needed in order to find the best result. This is again work in progress. For example, like this is a simple example, geo versus gene ontology. People know this, but sometimes we can see that they're not just simply abbreviation or something. People just choose to have a different ways of saying it, right? So we want to be able to link those in our search result. So as I mentioned before, there's sometimes, especially when there's multiple sources of information we can gather for a given resource, for a given tool. Then if they are inconsistent with each other, we may need a way to resolve that conflict. And this is actually the principle we set up to guide our decision. So basically, we want to always go with that one, the resource that is most reliable. Okay, that's a rule of thumb. After all of this, because as I said, in order to make the whole thing more sustainable and less error prone, we want to automate it as much as possible. But before we publish that, we need to go through a validation stage and to make sure that the information we derive automatically actually is meaningful and correct. So then basically we will send this back to the author or the original people who upload that PDF for validation before we publish that to the officially AZTEC. And the last item I'm going to talk about is our FRD publication mining, basically how do we automatically discover or populate the metadata table from the literature.
Okay, so I'm going to go over the publication mining, as I said. We have five main steps we're going to talk about. Identifying the tools. So out of all the articles on PubMed, only a small fraction of those are actually associated with publication of new tools. That's what we want to identify. And then from the text of those articles, we want to extract the metadata, summarize the tool, extract the funding sources, and then classify the tools belonging to a particular domain. So moving forward, we're going to be primarily sourcing AZTEC by journal mining. I think there's a lot of advantages of this over taking things from existing repositories. I mean, first of all, we're going to encounter fewer duplicates because each publication generally only has, or each tool will have a single publication and when it's originally published. And it can be more up to date. It can get things as rapidly as they're released. And also, we're adding a lot more new information by indexing tools that don't exist in other repositories. So we're going to be starting with the journals of the highest concentration of tools, like bioinformatics and BMC bioinformatics. These will be it'll be the easiest for us to identify the presence of tools in these publications because they release so many tools. They have a very structured way of writing their abstracts and their articles that describe the tools, whereas journals that release tools less frequently, they don't have such a structured, well-defined way of describing them, so it's a bit hard to identify. So we're going to start with these two in 2016, and then we'll move on in 2017 to cover journals with fewer tools in them. So the type of classification features we use for these publications, we look at the title structure and punctuation, the presence of words with an alternate word case that's not is either all caps or a mixed case, or including a lot of numbers in the word string. So some examples here, you can see a gene and a tool. They frequently have the same capitalization structure, the same presence of numerals inside the word, and they have the same sentence structure in the title of an article. So these could easily be confused. That's why at least in the case of genes, we specifically verify that the terms respective tools are not genes. Additionally, we look at the presence and frequency of keywords and synonyms in the title and the abstract, presence of URLs in the abstract, and the terms describing the URLs, and also the keywords and synonyms in the full text of journals where the full text is available. And we use a deep neural network for the classification. So here's an example of the features of features of either words that are generally associated with tools or words that we suspect to be a tool based on their case or some other feature like that. So you can see in this example, sequest here is a feature, Prolucid is a feature, and there are a few false positives like cross correlation, delta CN. Okay, we use the machine learning library Grobid to automatically extract metadata from the publications. So with this Grobid library, we can extract the tool name, authors, institutions, description, links, funding sources, and tags. And some difficulties we encounter. Not all tools are described by name in the title or the abstract. So here, this would be a challenging tool to identify because the title doesn't have any mention of the tool. The tool is in fact not named, but says an implementation of the method is available at listing the URL, so that would be something that we would still be able to identify. Using the text rank algorithm that Wei described, we identify the key sentences from both the abstract and the body of the publication, and summarize those to build brief descriptions of the tools that we can put into AZTEC. For funding extraction, we want to identify the grant numbers associated with these tools and include that as metadata in AZTEC. So to identify the type of candidate sentences that may contain funding information, we first filter them so that we only consider sentences that contain alphanumeric strings like these that don't exist in the English dictionary, that contain letters and numbers that could possibly be grant numbers. And then we search for text describing funding, like is supported by, for example, and also search for the presence of funding agencies within those sentences to determine if they describe funding. And we built our dictionary funding agencies from cross-reference. So here's an example. So here are two sentences, and they both contain these alphanumeric strings that don't exist in the English dictionary. So they would both be analyzed. But only the second sentence there mentions NIH, which we identified the funding agency, and includes the words "was funded by," which clearly describes the funding. Okay, so short-term goals. So things that we are currently working on right now in AZTEC, vocabulary control. We already mentioned the few areas where we're still improving that. Duplicate detection, tool similarity, ranking search results, identifying source conflict, validation, and publication mining. And then long-term goals, things we're going to move on to once those are all taken care of. We want to extend our PubMed mining beyond just bioinformatics to the entire population of journals. And we want to be able to automatically incorporate updates to the tools. So as a new release is pushed to GitHub, for example, automatically update the metadata in AZTEC. And we want to be able to challenging, we want to be able to suggest analytical pipelines. So for example, if there's a certain type of output format of one tool and an input format of another tool, or if we identify workflows described in publications in PubMed, we are kind of using the graphing library Neo4j to actually develop and show an AZTEC new novel analytical pipelines that you could suggest to the user. And here's our basic timeline for working on AZTEC. You can see the things we're currently working on, and then our long-term goals that will begin next year. And the acknowledgements, I'd like to thank everybody at the SciLab and at Dr. Ping's lab who's working on AZTEC.
Yeah, we also like to thank generous support from NIH, and also we get a lot of help from Penny's group.